In this video, we're going to be talking about linear models with boundary value problems. Specifically, I want to talk about eigenvalues and eigenfunctions. This is an extension of a concept that you may have already talked about in linear algebra with eigenvalues and eigenvectors. Very similar. So our solutions in differential equations are not matrices, they're functions. So we get eigenfunctions instead of eigenvectors. So let's go ahead and look at number 9 here. Y double prime plus lambda y is equal to 0. And we're given the conditions y of 0 is equal to 0 and y of pi is equal to 0. Now, talked about what the trivial solution is before. We're not interested in the solution y equals 0 because, of course, any derivative of that function is going to be 0, and you multiply by 0 and you're always going to get 0. So we're just know that we're not interested in when all of our constants are 0, which is going to make our y equal to 0. We don't want that. So we're going to assume that at least one of our constants is non-zero. We may solve and find that one of them is 0, but then the other one won't be 0, and the other part of the function will be 0. Okay, so we're going to look at this as m squared plus lambda is equal to 0. We're assuming that lambda is a positive number here. And again, that's to, you can look at the book to see the 3 cases, but if lambda was 0 or lambda was a negative number, then we would get the only solution would be the trivial solution. So we want lambda to be a positive number here so that we get something that looks like this. And m is equal to plus or minus root lambda I, giving us an equation in the form of y of x is equal to c1 cosine of root lambda x plus c2 sine of root lambda x. Let's go ahead and stick in our first condition here. Y of 0 is equal to c1 plus 0 c2, and that needs to be equal to 0. So c1 has to be 0. So that reduces y of x to be equal to c2 sine of root lambda x, like so. And we want to stick in pi here for x, c2 sine of root lambda pi. Remember that because c1 is 0, that means c2 cannot be equal to 0. It's arbitrary. It's allowed to be anything else that we want it to be. So for simplicity's sake, I'm going to let c2 be equal to 1 and just eliminate it from the problem here. That way, it's any constant multiple of this eigenfunction that we're going to get will work, which is what the value of c2 is telling us. So the easiest c to put in there is 1, and I'm just dealing with this other part now. So that's going to be equal to 0. And so the zeros of sine are when the argument of the sine function is an integer multiple of pi. The pi's will cancel, and root lambda is equal to n with, there's no lambdas on the outside, so my first n that I'm going to start with is 1. I start with the counting numbers unless there's a lambda that's on the outside that can multiply to give me 0 for an answer by choosing it as lambda. and then my answer will be will be based off of the whole numbers. So that means that lambda, my eigenvalues here, will be perfect squares, with n being 1, 2, 3, so on and so forth. So there'll be those perfect squares of 1, 4, 9, and 16, and so on. Let's come back to my function. Y of x is equal to sine of, and root lambda is n. So nx, and we're going to call this y sub n for my eigenfunction here. And that is how you solve one of these boundary value problems that is with regards to eigenvalues and eigenfunctions. There's other applications of boundary value problems in this section, but I'm going to let you deal with those in your engineering courses, because that's usually where beam deflection and things are discussed, as far as I know. So I'm just going to deal with the eigenvalues and eigenfunctions here. Y double prime plus lambda y is equal to 0. Y of 0 is equal to 0. Y prime of 0 is equal to 0. And y of L is equal to 0. So that has to do with beam deflection and so on, that capital L. You can see some examples of that in the book, but let's go ahead and get this. So again, m is equal to plus or minus root lambda I, making y of x equal to c1 cosine of root lambda x plus c2 sine of root lambda x, and I need y prime of x is equal to a negative root lambda c1 sine of root lambda x plus root lambda c2 cosine root lambda x. So y prime of 0 equal to root lambda c2, and that equals 0. So again, we are okay here with if lambda equals 0 or c2 equals 0. Let's go ahead and assume c2 is 0 right now and plug it in here. That eliminates the second part here. It makes y of x equal to c1 cosine of root lambda x, and makes y of L equal to c1 cosine of root lambda L, like that. We don't want c1 to also be equal to 0, which would give us y equals 0. So we want cosine of root lambda L to be equal to 0, which makes root lambda L equal to odd multiples of pi over 2, using 2n minus 1, so that the first one that I get, I'm starting at 1, will be pi over 2. And just ignore that. We don't want that. And that makes root lambda equal to 2n minus 1 pi over 2L. I can square that to say my eigenvalues that I'm interested in are lambda equals 2n minus 1 squared pi squared over 4l squared. And starting with n equals 1, 2, 3, so on and so forth, that means that what my yn x is equal to letting c1 be 1. This is going to be cosine of 2n minus 1 pi over 2l x, like that, for my eigenfunction. Let's go ahead and look at number 13. Prime plus lambda y equals 0. And that is y prime of 0 equals 0. And y prime of pi is equal to 0. So again, m squared plus lambda equals 0, m equals plus or minus root lambda I, which means y of x is equal to c1 cosine of root lambda x plus c2 sine of root lambda x. Y prime of x is going to be negative root lambda c1 sine of root lambda x plus root lambda c2 cosine of root lambda x. Y prime of 0 is equal to negative root lambda c1, positive root lambda c2, and that equals 0. So c2 equals 0, making y of x turn into c1 cosine of root lambda x, and making y prime of x turn into negative root lambda c1 sine of root lambda x. Okay, so now second condition here, y prime of pi is equal to negative root lambda c1 sine of root lambda pi. Again, we're going to let c1 be 1, so I don't really need to worry about that, but I can say negative root lambda is equal to 0, or sine of root lambda pi equals 0, so lambda equals 0, or root lambda pi is equal to n pi, which are the zeros of sine. And so lambda equals n squared, but this n here is going to be 1, 2, 3, so on and so forth. I also include the 0 here. So my complete solution, because 0 squared is also 0, I'll just stick in the n squared and start at 0, that my y of x is going to be negative n sine of n pi, n equals 0, 1, 2, 3, so on and so forth. Sorry, I just wrote y prime there, but I want y. So y of x is equal to c1 is 1, there like we said. So this is cosine of n pi. So going all the way back up to y right here, letting C1 be 1, cosine of root lambda is going to be n, with n being allowed to be 0 here. So on and so forth. Okay. But my eigenvalues are perfect squares. So I didn't say, yeah, I did say that here. Lambda is equal to n squared, including the perfect square of 0. Right? Going ahead here to number 13. Y double prime plus lambda y equals 0. So again, m squared. That is the one I just did. Sorry about that. On to number 15. And starting with a different looking function this time. Y double prime plus 2y prime plus lambda plus 1y equals 0. Y of 0 is going to be 0. Y of 5 is going to be 0. So getting the auxiliary equation set up here, m squared plus 2m plus lambda plus 1 is equal to 0. I'm going to keep the 1 on the left-hand side because that's part of my perfect square trinomial over there. I'll move my lambda to the other side, making this m plus 1 squared is equal to a negative lambda. M plus 1 is equal to plus or minus root lambda I, making m equal to a negative 1 plus or minus root lambda I. I now have an alpha and a beta. For my complex number. So my y of x is now equal to e to the negative x times a quantity c1 cosine of root lambda x plus c2 sine of root lambda x. Y of 0, e to the 0 is still going to be 1. So this is going to be c1. And then that's 0. So this is 0, reducing my y of x down to e to the negative x. C2 sine of root lambda x. I'm going to let C2 be equal to 1 to make this e to the negative x sine of root lambda x. Then we have y of 5 is going to be e to the negative 5th sine of root lambda times 5. So I'll call that 5 root lambda, and that needs to be equal to 0. E to the negative 5th is not 0. I can get rid of that. This is sine 5 root lambda is equal to 0. So 5 root lambda is equal to n pi. Root lambda is equal to n pi over 5. I'll need that to make my substitution. That makes lambda equal to n squared pi squared over 25, with n equal to 1, 2, 3, so on and so forth. And coming back to y of x, y n of x is e to the negative x sine of, and root lambda is n pi over 5x. Okay. Moving right along to number 17. It's going to be a Cauchy-Euler equation. Okay. So let y equal to x to the m, y prime equals mx to the m, y double prime is equal to mx to the m minus 1, m minus 1, x to the m minus 2. So this becomes m times m minus 1 plus m plus lambda equals 0 for my auxiliary equation. M squared minus m plus m plus lambda is equal to 0. M squared is equal to negative lambda. M is equal to plus or minus root lambda I. And since this is Cauchy-Euler, it's in the form of y of x is equal to c1 cosine of root lambda ln of x plus c2 sine root lambda ln of x. So now you see why we picked 1 for our lower bound here, because that's going to make the ln of x's become zeros. So that becomes c1 cosine of 0 is c1. C2 sine of 0 is 0. So this is equal to 0. C1 is 0. We have y of e to the pi. It's going to be, so all of this is gone. This is C2 sine of root lambda ln of e to the pi is just pi. And I'm going to let C2 be 1. That doesn't lose any generality because I can have other solutions to the problem that are constant multiples. So, and this needs to be equal to 0. So that means that root lambda pi needs to be equal to n pi, and root lambda needs to be equal to n. Lambda needs to be equal to n squared, with n equaling 1, 2, 3, so on and so forth. So my y of x is equal to sine of n x, sorry, n ln of x, like that. And again, it's that ln of x because it's Cauchy-Euler. One more problem here, I believe. Yeah, one more. Number 19. And while there are more problems like this in the book, I think we'll do fine just stopping here. I think this has given you a good overview of what boundary value problems are and how they're slightly different than initial value problems. So It's not that we're being given enough information to set up a system of equations and simultaneously solve for C1 and C2. We're given these boundaries, and that's enough information here for us to get a set of solutions that all would work, that just vary by a constant multiplier, and with these eigenvalues and eigenfunctions. So let's go ahead and make this Cauchy-Euler again. Y equals x to the m, y prime equals m, x to the m minus 1, y double prime equals m times m minus 1, x to the m minus 2. So this is m minus 1 plus m plus lambda equals 0, m squared minus m plus lambda is equal to 0, m squared is equal to a negative lambda, m is equal to plus or minus root lambda I. And that means that y of x is equal to C1 cosine of root lambda ln of x plus C2 sine of root lambda ln of x. Again, we're going to let x be 1 because that makes these ln of 1s go to 0. Cosine of 0 is 1. Y of 1 is going to be C1 plus 0. That needs to be equal to 0. So this whole part drops out. Y of x is equal to, and I'm going to let C2 be 0. I'm sorry, be 1. Sine of root lambda ln of x. Now be careful that this says y prime. Here is y prime of e. So y prime of, I'm on 19. Sorry, so that one said y prime of 1 is equal to 0. So I need to find y prime before I continue here. So y prime of x is equal to negative root lambda C1 sine of root lambda. This is over x. X plus root lambda over x, C2 cosine of root lambda ln of x. So y prime of 1 is equal to negative root lambda C1, this is all 0. So this is root lambda over 1 is root lambda. C2 cosine of 0 is 1. That needs to be equal to 0. Yes. So C2 is 0 still, and that eliminates that part. So y of x is equal to C1 cosine of root lambda ln of x, and that makes y prime of x equal to, C2 is gone, so this is negative root lambda over x sine of root lambda ln of x, and I need y prime of e squared. So y prime of e squared is negative root lambda over e squared sine of root lambda ln of e squared is 2 root lambda. So because I have a lambda on the outside, lambda is allowed to be equal to 0 to give me this 0 here. So that means that 2 root lambda equals n pi, the zeros of sign, and root lambda is going to be equal to n pi over 2. Lambda is going to be n squared pi squared over 4. N is going to be allowed to be 0, 1, 2, 3, so on and so forth. So my y of x, allowing c1 to be 1, is going to be cosine of root lambda being n pi over 2 ln of x. Like so. And that should be it for this video. We'll end chapter 5 there, and we'll start with 6.1 next time, which is just a review of power series. And I'll talk about some techniques and things with power series that you may not have talked about in Calculus 2 that are going to be important here in differential equations with reindexing, power series, and things like that. So see you for 6.1 next time.